हेलो एंड वेलकम बैक। सो नेट 2024 में जो क्वेश्चंस आए थे इलेक्ट्रोडायनेमिक्स के रिगार्डिंग, सो वो हम करने जा रहे हैं आज। एंड द फर्स्ट क्वेश्चन इज a sphere with uniform charge and mass density having total charge q and mass m rotates about an axis through its center with angular velocity omega. The ratio of its magnetic dipole moment to its angular moment is. So ये चार ऑप्शंस हमारे पास क्यों है? सो बेसिकली हमारे पास जो अरेंजमेंट है वो इस तरह का है कि एक रोटेटिंग स्फीयर है, सॉलिड स्फीयर। ओके, सो इट इज रोटेटिंग सपोज with angular velocity omega, and suppose its radius is r. So I have to find what will be the ratio of mu over L. That is the magnetic dipole moment over the angular momentum. Angular momentum. Okay. So for this case, we know L. L will be simply equals to point of inertia times omega, and we know omega for solid sphere is 2 by 5 mr square, so 2 by 5 mr square omega. So this is L. Now we need to find omega, this mu, that is the magnetic dipole moment. So we know mu is simply the current times the area of a simple ring. Suppose if we have a ring in which current I is going okay, whose radius is r, then mu is, is simply I times pi r square. But we don't have simple ring, we have solid sphere. So this is our solid sphere. So let's try to find mu. So okay, so mu for solid sphere, mu for solid sphere. So before we find for solid sphere, we'll first of all find for shell, mu for a shell. Okay, we have a spherical shell. We'll try to find mu for that case. So suppose we have a shell like this. We have a shell and this is the radius r, and we want to find mu. Okay, so let's take a simple current ring. Like let's take a ring. So this will be the ring for our case. Okay, so this is our ring. We'll find, we know d mu, that is what is the dipole moment for this ring. So it will be simply the area, that is, so this is small r, it will be pi r square times the current, that is di. Okay, right? So this we know, but to find the magnetic dipole moment for this whole shell, we need to integrate it. So mu will be equals to integral of this, so that we have to integrate. So that will become integral pi. Now r square is, let's write r square for the moment. Now what is di? So di di is simply uh, surface current times dl. So this is the small dl distance, dl. Okay, and we know k is, if we have sigma as surface charge density times v. So di will be equals to sigma v dl. Okay, and what is this dl? This dl equals to r d theta, right? So we can substitute now. So we can simply substitute here that mu for a shell equals to, let's write shell here, mu for a shell equals to integral, okay, so this is di pi r square sigma v dl. Okay, so I can write it like this, integral pi r square sigma. Now v is the velocity, okay, because every point on this ring will have the same velocity, and that velocity will be equals to omega times r, right? So omega r, and what is dl? Dl is rt theta. Rt theta. So I have to solve this integral to get the angular, dipole moment for the shell. So, and we know r. So r will be equals to, because this is right triangle, so we can simplify this r, because this is r and this is theta, so this will be r sine of theta. So in this triangle, so r sine of theta. So then I can take constants out, so pi and sigma omega r4 integral, then it will be a sine cube theta d theta. Okay, and theta runs from 0 to pi, so it will be sigma omega pi r to the power 4, and we know this sine cube theta integral, so integral sine cube theta d theta, so it will be equal to minus cos theta plus cos cube theta by 3. So you can solve it, and if we plug these numbers, so we'll get 4 by 3. Okay, so I can write mu for a shell equals to 4 by 3 sigma omega pi r to the power 4. Okay, so this is the dipole moment for a shell. So dipole moment for a shell we know. Now what about dipole moment for a solid sphere? Because we have actually the solid sphere. Okay, so if we know for a shell, we can integrate simply. So mu for a solid sphere, solid. So it will be integral of these. Who we can take now small shells, so that we can make a big solid sphere. So that will be integral. So 4 by 3. Now sigma will be turned to rho dr. Okay, then we have omega pi r4, right? So I can take constants out, 4 by 3 rho omega pi integral r4 dr, and here r will change from 0 to capital R. Okay, so mu for a solid sphere will be equals to 4 by 3 rho omega pi r 5 by 5. So we got our angular, type moment for solid sphere also. But what about this rho? Rho is the total charge density, so that can be written as rho equals to q by 4 by 3 pi r cube. Substituting, we will get mu for solid sphere equals to 4 by 3 omega pi r5 by 5, then rho, so we have q over 4 by 3 pi r to the power 3. So you'll get cancellation here. So let's see what will cancel out. So pi cancel out, 4 4 3 3, and we have r3 here, so only r square will remain. So mu for a solid sphere equals to q omega r square by 5. So we got this one, and we also have L also. L was equals to 2 by 5 m r square omega, right? Now if you can take the ratio, so mu by L equals to q omega r square by 5 divided by 5 m r square omega. Again cancellation will have happen here, so omega cancels out, r square cancels out, 5 cancel out, so the answer is simply q divided by 2m. So this is our answer, q by 2m. Q by 2m. That was third option.
So the next problem is a static charge distribution produces an electric field given by this E equals to Q by 4 pi epsilon naught e to the power minus br divided by r cube times r vector. While Q, B greater than 0 are constants, the charge density of the distribution is given by. So हमारे पास इलेक्ट्रिक फील्ड गिवन है और हमको ये बताना है कि चार्ज डेंसिटी क्या होगा. So let's start. So we can use simply the Gauss's law. So we can use Gauss's law here. Gauss's law in differential form, that is divergence of E equals to minus, not minus, it's rho over epsilon naught. Okay, so E is given, we have to calculate rho. So that means rho will be equals to epsilon naught divergence of electric field. Now we know divergence in spherical coordinates. So divergence in spherical coordinates is given as, if we have only the radial component, 1 over r square d by dr of r square times the radial component. Okay, so we can simply substitute. So we get rho equals to epsilon naught, then divergence of what is electric field. So electric field is, so our electric field is E equals to Q by 4 pi epsilon naught times e to the power minus b r by r cube times r vector. Now we can uh, just do here like this. We can simply write r vector by r square. Okay, so this is our electric field. Now we'll simply substitute this in this equation. So rho equals to epsilon naught divergence. So I can take constants out. Q by 4 pi epsilon naught. It's simply 1 over r square d by dr of e to the power minus b r by r square. Or you can write epsilon. Epsilon gets cancelled out. So rho equals to Q divided by 4 pi r square. Now differentiation of this. Okay, so there was also r square here. So r square will also get cancelled out. So differentiation of e to the power minus br will be simply minus b e to the power minus br. Okay, so this is our rho. So our rho equals to Q divided by 4 pi r square minus b e to the power minus br. So, but this is not the full solution. Why? Because if we look at the electric field, so our electric field, suppose this is our electric field, okay? This electric field behaves like a point charge, because when R is, suppose, very, very small, R is almost equal to 0, then you can write electric field as Q divided by 4 pi epsilon naught, that's e to the power minus b r, b equals to almost equal to 1. So it will be R cap by r square. So it means when R is very, very close to the origin, the electric field will behave like a point charge. So we have to compensate for that, okay? Because the density will shoot up. So what we have to do? We have to compensate for the point charge. So compensate for the point charge at the origin. Point charge at the origin. At the origin. So for that we know, like because we have to do the divergence of r cap by r square. So we know for that it will be 4 pi the delta function or the Dirac function of r. So that means we have to add here the contribution. So that means we have to add the contribution. That means we can, okay, let me write it like this. So we have to add the contribution of this point charge. So that is plus, okay, this minus will be inside. So 4 pi delta of r. Okay, so this is the full solution. So why I added this part? So that the point charge will be taken into account. Okay, so that's it. So if we look at the answer, so it's the answer 4. Okay.
So another question from electrodynamics was, an electron enters a region of uniform electric and magnetic fields E naught and B naught. E naught and B naught are mutually perpendicular to each other. Initially, E naught is so adjusted that the electron suffers no deflection. Okay, so electron suffers no deflection. E naught is then switched off and electron moves in a circular path of radius r. The speed of the electron and its charge to mass ratio would be, okay, so no deflection, no deflection. Okay, so if there is no deflection, that means forces are balanced out. So that means there are two forces. One is the electric force, so that we can write Q E naught will be equals to the magnetic force, that will be Q V cross B, because they are perpendicular, so we can write simply VB. So V times B naught. So it gives us the velocity will be equals to E naught by B naught. So this was the first part of it. So this is speed, right? Now what we have to find, charge to mass ratio would be charge to mass ratio. Okay, so charge to mass ratio, charge to mass ratio. Now we know electron moves in a circular path, so it's moving like this. Okay, so let's make an electron here. So this is our electron. It moves in a circular path, and let's just suppose that magnetic field is coming out of this plane. So magnetic field is out, coming out of this slit, and the electric field is 0, and then the force will be so force will be Q times V cross B. So V is in this direction. Okay, so this was the path, and this is V, and V cross B will be uh, okay, so force will be in this direction, okay, toward the center. So that's why it's moving in the circular fashion. So we can write this force towards centripetal force, that is M V square by R equals to this force Q times V naught. So we'll get V equals to, okay, wide point charge to mass ratio, that is Q by M. So that means Q by M will be equals to V naught divided by um, M, no, sorry. So we'll have Q by M. So Q by M equals to V times V times V divided by R times B naught, right? And we know V is E naught by B naught, so we can write E naught by B naught. So E naught by B naught squared. So this will be our charge to mass ratio. E naught by R B naught square. E naught by R B squared. So that is option number 3. So one more question from electrodynamics. So one more question from electrostatics was, consider a spherical region of radius r by 2 centered at the origin of the coordinate system. 3-point charges, each of magnitude q, are placed at 0, 0 r, 0 r 0, and root 2 r 0, 0. What is the magnitude of the average electric field over the spherical region due to these charges in units of this? Okay, so we have basically a spherical region. Let's draw a spherical region. So it's like this. So this is X, this is Y, and this is Z. And we have our spherical region. Let's just suppose this is our spherical region of radius r by 2. Okay, so this is r by 2. So first charge is at 0 r. So let's just put the first charge is at here. The second charge is at 0 r 0, 0 r 0 here. Okay, so this is 0 0 r, this is 0 r 0, and the third charge is at root 2 r 0 0. So again it will be here, root 2 r. Okay, so it's way here. So root r 0 0. And what we have to compute? We have to compute the average electric field over this vertical region. So average electric field. So if we look at the formula, average electric field. So average electric field means, so first of all we calculate the flux over the whole surface. So that means integral E dot ds. Then we divide by the surface area 4 pi r square. And now we know integral E dot ds using Gauss's law. Integral E dot ds equals to charge inside E dot E dot ds equals to charge inside by epsilon naught. Now, charge inside, there is no charge inside this spherical region, so that means Q inside is 0. If Q inside is 0, that means this integral is 0. This integral is 0, that means the average electric field over this spherical surface is 0. So it's option number